Yeah, so thank you very much for inviting Lightbend and me to come and speak. And thank you very much for allowing me to speak in German. In English, sorry. Yeah, let's get that right. We'll all get a lot more out of this if I speak English. Funnily enough, one of the few phrases I know in German is Einfach Klasse, which is the name of the textbook that I was given from which I should have learnt German when I was at school. So there's a certain irony there. And I apologise also if I start to cough a lot. I seem to have developed a throat infection from my children, who are really efficient germ incubators, it seems. Just need to weaponise them. So yeah, we're talking about microservices in the first half of this presentation, and then more specifically about Lagom, which is Lightbend's framework for making you, or trying to make you do microservices the Lightbend way, which we believe is the correct way. So we'll start with what the business problem is. It's very easy in these kind of talks and in development generally to get tied into the technical problems, you know, this crashing or that configuration. And we get taken away from the reason we're all here is it's great to work with cool new technology, but that's not what pays the bills. What puts food on the table and the roof over your head is solving business problems. And that's really why we're all here, one way or another. So here's some business problems that are associated with the monolithic application. It costs a fortune to keep running. It crashes a lot. It takes a long time to load pages. And feature requests are taking a long time to execute and deliver on. And here's the technical problems. These are the ones we're actually interested in. We need to redeploy everything to change one component because they're all tightly coupled. Everything's really tightly associated with everything else in the system. We find it's difficult to scale, increase in operational costs. We see monolithic applications that can't deploy new releases within a year. 9 months can be like kind of an average, and that's crazy. Like, how are you supposed to react to any kind of business situation or a competitor or anything in 9 months to a year? So we need to solve these problems so that we can use cool new stuff and that the business can grow and scale. One of the very common problems we see actually is this situation where one particular part, one system within this monolithic application is taking up a huge amount of resources. It's causing all the latency, it's hogging all the CPU processing power. And we can't scale that because of problems with other services and this, that, and the other. So we need to solve this problem mainly. We have patterns at Lightbend where we can come in and consult with you and move you from one thing to the other, but this is one of the major problems we have. What we end up with the monolithic application is what's been called popularly the big ball of mud. Everything's tangled in with everything else. You can't pull on one thread without something falling off at the other end. It's like the clown's car, you know, when you press the horn and the door falls off. So you see this quote in a lot of Lightbend presentations because it's provocative and it gets a bit of tension going in the room because you're all doing it wrong. Right? You're not, but we think there's a better way to do it. So by traditional applications, we mean the monolith. We mean Java EE, we need WebSphere, we need whatever you want it to mean, PHP, Perl. And they're obsolete in the sense that there's a better way to do it, and that things are now at such a scale and we need to react more quickly than we can. And so they're becoming obsolete in that way because new technologies are taking over, and there are other businesses in your domain who are ahead of you doing this already. And that doesn't apply to you specifically, but whoever we're talking to, whether you're an airline, whether you're a cruise company, whether you're a bank, whether you're in whatever business domain, there's someone else doing it better right now, and we all need to catch up. And this is one of those slides. Oh, no, it's not. Haha. I thought I had some slides that, as Ben experienced, now we can't build them step by step because we're in a PDF. So how do we solve the problem? We've defined our problem. Where do we go next? And one of our founders, Jonas Berner, in around 2014, 2015, wrote something called the Reactive Manifesto. He'd spent a lot of time working with various ways of trying to scale the JVM, and he'd found that there were intrinsic problems going on there which couldn't be solved with the standard way of doing things. And so he went back to basics and forget about technology, forget about writing code, let's break the problem down and think about what we need to do. So responsiveness is our aim. What we want to be is responsive. Whatever happens, we want to respond to the user in a timely fashion. And how do we become responsive? We need to be resilient and elastic. No matter what goes on, what failures happen, we need to try and recover from them in order to be responsive. So, you know, if people start randomly pulling cables out of machines in a data center, if winter comes and the dead rise and march south of the wall, we need to accommodate ourselves to that situation. Obviously, there's an upper limit to resilience. We also want to be elastic. We want to, if there's a lot of resources, a lot of requests coming in from users, we want to scale up. But we also want to be responsible utilizers of our resources. We want to save money, basically, and scale back down when the load is less. So we want to be responsive, and we be responsive by being resilient and elastic. And the way to be resilient and elastic is to be message-driven, is to isolate and decouple all of our services, all of our software components, and only allow them to communicate by asynchronous, non-blocking messaging. That's what we believe. And the fact that we're still around a few years later and we're having massive customer success suggests that we might be onto something, but who knows? So this is the takeaway from this is the bullet point to take away from this presentation, is that everything should be message-driven. Oh, excuse me. So if we go back to that first slide about the business problems, we can map these business problems to those reactive components, those reactive statements. If an application is costing a lot of money to keep running, that's an elasticity problem. If it crashes, it's resilience. If it's taking too long to load, it's responsive. How do we solve this page load problem? We go back and we try and be elastic and resilient, and that means being message-driven, and that will make us be more responsive. That will solve the blocking problems in the application where it's waiting for responses from other services, which are waiting for responses from services, and so along a chain, which is causing these 10, 15-second page loads. And if we do all of that, then we can ship features much more quickly, and we'll show you how in a second. So what should microservices look like? If they shouldn't look like that, sorry, what should they be like? I need to keep my hands still. They should be separated. So it's easy to say, yeah, we will take the same monolithic application and we break apart into these services, and we don't let them talk to each other, and we don't let them interact, and we don't do anything, and we're just completely isolated. Solves the problem. It's not very effective, but it does solve the problem. We make them autonomous is the next step. So we build up from this decoupling. We allow them to scale independently. And this solves another problem of the monolith, where if all of your systems are in one big application blob, they all have to be more or less on the same stack. You know, everything has to be Java, everything has to be whatever you're using. If you break out all your services and make them independent and autonomous, self-governing, then they can be implemented however you like. If you bring in a new service that's doing something that Python does really well, write in Python, and it doesn't affect any of the other services because they're only going to communicate by message passing. So we have to let them communicate. So we've got 3 ways to allow them to communicate. And these are in slightly different order, so let's just jump. Yeah. So in an ideal world, this would be the best way to allow everything to communicate. We completely decouple everything. We stick an event bus in the middle. We'll use Kafka because it's brilliant and that's what you should be using. Don't really know why you should use anything else. Granted, we have nothing to do with Kafka as a company, but it's brilliant, so go with it. We have our services dispatch events. And by events, we mean facts, things that have happened in the past. Not a promise to do something in the future, not a command to go and do something and give me a result, but events that have happened. So these services, by the way, I should have mentioned, this is from one of our examples for Lagom, which you can go and download from GitHub and get up and running. And it's an eBay clone, essentially. So we have users, bids, items, transactions. It's an online auction system that is fully functional, and you can clone it, run it, fork it, whatever you want to do, and learn about Lagom. So this is part of the system. When a bid is placed, an event, the bid service dispatches an event, it goes onto the bus, and now 0 or more other services can consume that event, and we have no coupling. But we don't always want to do that. We sometimes need to ask a question and get a response. So it's the difference between asking and telling, which is part of the Cqrs API, which we'll move on to later. But when you tell someone something, you tell them and off you go. We don't care what the response is. When you ask for something, you wait for the response. So in this case, we want to ask. And the way to do that is to have a public API for all your services and communicate through that and that only. And we see a lot of setting up an API and then, oh, but quick, I need to do something quickly, so I'll just go in through the back door into the and now we couple up, and now we have problems. And now that guy who wrote that leaves, and now there's a feature where there's a problem. No one knows it's there. So we work through the public API. We're asynchronous and non-blocking at all times, which is by default in Lagom, and we're all happy. Now, the last way of communicating, which is kind of specific to Lagom right now, it's common around, excuse me, sorry. I mean, it's not specific to Lagom, we're not the only people that do it, but it's a nice feature of Lagom is to be able to stream and to be able to pass streams along from service to service. So in this case, there's actually a better diagram of this, but this will do. This user is, and this is another example, by the way, from Lagom, from the GitHub account. And this is a Twitter clone, if you haven't already spotted it. We've got friends, we've got chirps. It's chirper, not Twitter. So we chirp. And we have an activity service, which is just really a proxy for these other two services. If I want to get, or this user is me, I want to get all the tweets from my friends, and I want a continuous stream so that when a new tweet is tweeted, a new chirp is chirped, sorry, TM, I will receive that new chirp. So the activity service gets the user, gets me from the friend service, and then it gets all my friends. And then it makes a request to the chirp service, which gives it back a stream, which it now passes back to me. So now I have my stream. And this is an Cqrs stream. It's, we'll go into reactive streams, but Cqrs streams is fully reactive, so it's non-blocking. And it's, in this case, it's over a TCP connection. It's non-blocking right back down to the TCP layer. So if I'm streaming something to my web browser and my web browser is slow, the server will stop pushing events down and stop flooding me, and everything sits nicely, waits until the consumer can consume. And lastly, we want to isolate all our data. This is another thing we see, a really, really common problem we see with companies moving from monolith to microservice is they have created a nice set of defined services. They're all nicely encapsulated, they're all autonomous, and they all connect to the same data system. They all connect to the same data store, and now they all block each other because now we're locking rows, tables, whatever. And we have a huge problem then. And we've actually got a term for it, which is horrible, but it's called the microlith, which is a set of small monoliths which all go to make up one big monolith again, and all you've done is recreate the same problems for yourself, but now you've got lots of services, so there's more code creating the same problem. So it's just something to avoid, is that a microservice should own its own data, and we'll get to that in a moment. So our definition, Lightbend's definition of a microservice, or a set of microservices. One microservice on its own is no microservice at all. These things, they're like royalty, they come in gangs. So a system of autonomous, collaborative, distributed services makes up a microsystem. And it's yet another buzzword we're trying to push, is microsystem. So how do we do it? How do we do all this magic and make customers massively successful? We use Akka. And Akka is the basis of everything we do at Lightbend, pretty much. It's an actor model implementation for the JVM. Begins with Erlang back in the 80s, which begins with the actor model back in the late 60s. Yeah, maybe. No one's arguing with me, so yeah, it's 60s. So, in the actor model, we don't have a class where we call methods. We don't have an instantiate a class into an object and then invoke functions on it. We don't do any of that. We pass messages. It's hierarchical. So we start with actor A. Actor A creates a child actor, and child actors can create their own child actors, and everything's supervised all the way back up. So if E goes down, if E processes a message which throws an exception which is uncaught, it doesn't have to deal with it. Its parent, its supervisor deals with it. And it deals with it in the form of a message, because everything's a message. So C receives a message that E went down, and now C can do something about it. Do I destroy all my children and start them up again and try again with the rest of what's in the mailbox? Do I just give up? Do I fail myself and send a message to my supervisor that I've gone wrong? There's various different ways of handling failure in this scenario, but it's managed, is the point. And there's a difference here between failures and errors. Errors are something we can manage ourselves, we can cope with, we can expect, we can use try-catch blocks, we can check for null, you know, we can do all these types of things and try and guess at what might go wrong, but something's going to happen that we've never predicted, and that's a failure, that's the unexpected, and that's what we can manage here. So yeah, it's message-based. Messages consumed by an actor one at a time from a mailbox. So every actor has a mailbox, and it basically just sits there and takes a message, does something with it, checks what type it is, what it should do, and moves on to the next message, or waits for a message to arrive. And we have very simple semantics. I mean, this is the Scala API, so it's super simple. Actor, bang, message. That sends that message to that actor. But in Java, it's slightly more verbose. It's actor, tell, message. So it's still pretty straightforward. But as I say, you never interact with the actor directly. You only ever send it messages. And the way we do that is to only talk to the actor ref. So when you use an actor system to create an actor, you get back this actor ref object, and then you send the messages to that. And that manages whether the underlying actor is on the same JVM, or it's on another node in a cluster, in a database somewhere on the other side of a data center on the other side of the world. You don't care, as a programmer, where it is. You just talk to it, and the clustering is a configuration issue. Your code looks the same. So it's a really nice way to do it. And you control the deserialization and serialization. You can use JSON, protobuf, Avro. You don't want to use Java's inbuilt serialization because it's extremely slow, and you actually get warnings in Akka if you try and use it. We try and steer you away from that. But expertise in a framework does not guarantee progress towards your goals. This is a quote from one of my colleagues at Lightbend. Basically, if you're a really, really good Spring developer, it doesn't necessarily mean you're going to build really, really good microservices. If you're a really good Perl developer, you could create fantastic microservices. The framework itself is not what makes you good. It's having the knowledge of how to build these things at scale. And having said that, we've now written a framework. But what we try and do is use that framework to guide you towards doing it the right way, doing it the Lagom way, yeah, the Lightbend way, because this is what we've learned from our customers. This is what we've learned is the right way to do it, because this is how you succeed. And when you do it different ways, problems creep in and you tend to not succeed. But just a quick note here about the word microservices. It's a real big buzzword in the industry now. Everybody's talking about microservices. And we do see people get sucked in a little bit by the micro part. And they break it down and they come up with tiny, tiny services which are too small because they've broken up this bounded context. But now they're having to talk to each other too much. And what we want to do is have some bright spark on the mailing list. Basically came up, a Swedish person came up with the name Lagom, because Lagom is a Swedish word which means just the right amount, not too little, not too much, as in, you know, the Three Bears type situation. And there was big talk about having this be Lagom services, but microservices just kept on going. So it's just a point to remember that it's called a microservice, but it could be pretty big. It's defined by the business problem. We always have to go back to the business problem, remember what we're trying to solve, and then bound our context around that. So we have to come to Lagom. So you can see even from the logo, we've got the Three Bears there. Normally there'd be a demo, but I can't connect my computer. But what's probably a good idea is just to show a couple of screenshots of just what Lagom actually looks like in the IDE, just so you have an idea, and then I'll, how much time we got? Yeah, and then I'll just jump on to some other little bit more theoretical stuff. Oh no, we're going to go straight to the theoretical stuff. So, one of the big problems with microservices and moving away from the monolith is handling its fault tolerance and handling the persistent side of things. We tend to have one big database, talk to it constantly, and it becomes a point of failure, or at least a point of contention. So, there's a very different approach taken in Lagom. So if we just roll back again and remind ourselves that a service always owns its own data. So one service is never going to talk to the same database as another service. And this also is an advantage in that we can use different data stores for different services. They don't all have to use Cassandra. They don't all have to use Postgres or Oracle. We choose a slightly different approach. Because we've seen it succeed. And everything I'm going to talk about here in Lagom can be done in pure Akka. And we've seen a lot of people do it in pure Akka, and we've done it ourselves in pure Akka, but it's difficult, it's hard. It takes a lot of understanding as well as learning the actor model itself. So what we try to do is make it easier, but it's worth understanding the theory behind it. So we talk about persistent entities, and this is how we persist things. Actors are really good at representing things in the world. So if you have all of your users, they're not going to fit on a single machine. We can spread them out across many, many machines, and each user could be represented by a single actor. We can have billions of these things, and it's fine. And we have users with billions of actors live on a cluster at any one time. So this kind of size isn't a problem. The size of your domain is not an issue. So each persistent entity corresponds to an aggregate root in domain-driven design, which means it's something it's consistent across transactional boundaries. What that means is that if you have a user service, your user when you create a user, it doesn't need to go to another service, do something, and when that succeeds, come back and finish off creating a user. It means it does it all within the user service. So what we use to persist all the data in our persistent entities is something called event sourcing. So we don't have a single database, which is just the now of the system. We query it, and it's just what's happening right now. We store everything, because storage is pretty cheap. So we've added a friend, we've removed a friend. These are commands. These are telling the service to do something. They're telling the persistent entity to do something. Add a friend. So Bob adds a friend, Peter. He does some work. He updates his internal state to represent I now have a new friend. And it persists an event. Again, we go back in time to the past tense, friend added. And this goes into a log. And now everything that persistent entity does dispatches an event, goes into a log, and now we have a bulletproof audit trail of everything that happened to get us to the current state of the object. If something goes wrong, we can replay that event log and get back to that same state. So we're now fault tolerant. We also have this audit log, which is stored. It's in Cassandra or whatever we want to store it in, Kafka, whatever. And we can go back to this now and apply analytics retrospectively. If we have a way of analyzing the ways in which people friend and unfriend each other, and we change that algorithm, we don't have to wait and apply it to new data as people friend and unfriend each other. We can go back and apply it to the history of everything that's happened, everyone who's friended and unfriended since the beginning of time. So there's a big advantage there. So if we add and remove a friend, Bob has no friends, poor old Bob. But he does know that he had some in the past, and he knows who it was and when it happened. So as I say, the benefits are around having this bulletproof auditing, and we see a lot of value in that from banking customers, and obviously that we know exactly why this bank account got to this state. We can trace back, we can see if there was a problem, or we can prove what happened. And also here, the traditional database is just this snapshot, really now. This is much more powerful than just having a database, because once you change something in the row of a database, it's gone forever. But here we can reproduce any state from a history. So we've got our event sourcing, we know what happens, how do we manage these things in a cluster? So in Akka, as in Lagom, we can create a JVM, an actor system on a JVM on a single machine. Then we can create another actor system, either in that JVM or in another JVM on another machine, and we can tell them to talk to each other, and now they will self-organize. And we can have hundreds, thousands of nodes in these clusters, each with millions of actors within them. So it's pretty powerful. There are all sorts of issues then around the split brain problem. So if there's a network partition, and there's solutions there for how the cluster can decide whether it's the correct side or not, and we can down one side and carry on running. But as you see, yeah, we've moved away from this CRUD approach to having everything in memory. And there are a lot of optimizations around that. Obviously, we don't want to have everything in memory because we said we want to be good citizens and we want to utilize resources correctly. Sorry, I'm just aware of time. Okay, so we can snapshot things. We don't have to roll back for the entire event log. We can snapshot and just replay from there. We can passivate an actor. If an actor hasn't been interacted with for, say, 3 minutes, we can just down it and bring it back up later on. And we've got the event log and the snapshots to work from to bring it back up later. So we can just down something and worry about it later. If that user logs out, we won't worry about it. When they log back in tomorrow, we can resurrect their state and they're off to the races. So in clusters, we don't just start up a cluster and there it is. We can really efficiently add and remove nodes from a cluster. And those persistent entities will now rebalance themselves across the existing nodes. So if suddenly half our users log out, we can just take those nodes down, and the Akka will manage just resharding everything. So it's a really nice system. If something breaks, if something goes wrong, if one of the nodes goes down, if if a network cable's pulled out, for instance, if a network cable's pulled out, something goes wrong, that node goes down. Those entities that were on that node will just be brought up somewhere else on another node. So the fault tolerance is so built into the system. You have to work hard not to be fault tolerant with Lagom. So the last note, we've got Lagom persistence, we've talked about event sourcing, and we've got all our events in a log, we know what's happened, but how do we query it? If we don't have a database, what do we do? And this is where something called Cqrs comes in. And it's a horrible, horrible acronym. I really don't like it because it's not descriptive at all, in my opinion. But it stands for Command Query Responsibility Segregation. It's rubbish. So the fundamental idea is that you have a write side, which is what we just discussed, the event log. It's the truth of what happened. And then we have a read side, which is customized to how we want to read it. So we've probably all experienced having a low-level domain model in a database somewhere where when you want to write something to it and read something from it, you're always doing transformations. It never quite fits what you want to do with it, but it's beautiful. It defines exactly your domain and all the elements within it, and it's totally normalized to the nth degree, and it's a work of art, but you have to work to get things in and out of it. You've got to transform things into JSON. You should do complex queries to extract information. With this, you don't. With this, when an event is persisted to the event log, it's also dispatched out onto a stream somewhere. And subscribers can take that event, like friend added, friend removed, and execute some SQL on Cassandra or Postgres or whatever you want, depending on your use case. So, and you can have more than one read side. So for every way in which your data domain model needs to be queried, you can pick the perfect solution for your persistence. And you can put your data into it, you can update it, and now it's hot there in whatever you want it to be, ready for being queried, with the minimum amount of transformation required. So now we're more responsive. We're not having to wait the extra milliseconds for the JSON encoding or the complex query that maps loads of tables to each other. So it's a huge benefit. But the drawback here is around consistency. We're very focused on being highly available. So we've got the CAP theorem thing, consistency, availability, partition tolerance, and partition tolerance kind of goes with everything because we're talking about distributed systems, so we can put the P to one side. We have to have that. So now we're in this C or A situation. We have consistency or availability. And what we say at Livebend is that you probably don't need high consistency in a system. You don't need the immediate consistency. There's ways around that. You're better off going for availability and then finding a way to deal with the consistency. So if an event goes into the log, there's a delay. How long is that delay? It depends on how your system is implemented. It could be a few milliseconds, it could be half a second, but there's going to be a delay there. But there are ways around this, which I can go into another time. Or you can read online, because the time's running out. But that's the kind of, sorry, I'm losing the thread. That's the important point to remember is that while this is fantastic, it is not immediately consistent, and that's what a lot of people find difficult. We're all used to a consistent world, only we're not. In software, we want to be consistent, but the real world isn't consistent. The real world, there are delays. People make promises and break them. And our software should reflect that. And when you start getting in, this mindset of eventual consistency is fine and we can work around it, you start to see it everywhere and you start to realize it's not that big a deal. We've just been stuck in this mindset for a while. And it's taken us away from writing efficient distributed systems. So, just a quick recap. Yeah, we keep everything in memory because memory's there, it's cheap, and we can do that, and it makes everything hot and ready to be used immediately. Store everything as a state change, replay everything if we want to recreate it, and eventual consistency. And if you don't want to use event sourcing, which I've been talking about for the last 10-15 minutes, you don't have to. As long as you're not blocking, it doesn't really matter. It depends on your use case. It depends on the business problem you're trying to solve, remember. So you always have to go back to the business problem and pick the best choice. If you're not ready, you're not sure about event sourcing, don't use it. Stick with what you know, stick with what you're confident with, and just do it the right way for now, and then you've always got the choice to move on later. Oh, that's it. And we're done.